Corrosion is a natural process that affects many materials around us. It is the gradual destruction of materials, usually metals. This destruction happens because of electrochemical reactions with the environment. Think of it as a slow, persistent decay, a relentless force of nature. While it can affect various substances, metals are particularly vulnerable. We often refer to corrosion the cancer of metals. This is a fitting description because, like a disease, it can spread unseen. It starts from surface but weakens the material from within, compromising its strength over time. The underlying reason for it is quite fundamental. It is essentially metals attempting to revert to their more stable, natural forms. When we extract metals from their ores, we invest a significant amount of energy. This energy transforms them into the refined, useful metals we use for construction and manufacturing. However, these refined states are often less stable than their original ore forms. Corrosion is the process by which metals release this added energy. They react with elements like oxygen or sulfur in their surroundings. Rusting is the specific term we use for the corrosion of iron and its common alloys, such as steel. It is an incredibly familiar phenomenon, a reddish-brown coating that appears on neglected metal objects. For this common type of corrosion to occur, 3 key components must be present: iron, water, and oxygen. The mechanism behind rusting is fundamentally the formation of small electrical circuits on the surface of metals. Small electrochemical cells spontaneously form on the iron. If the iron surface has any imperfections, this area can become an anode. The anode is the surface area where oxidation or rusting occurs. The surrounding, more intact part of the metal surface then typically acts as the cathode. The moisture present acts as an electrolyte, allowing ions to flow between these 2 regions. At the anodic sites, iron atoms undergo oxidation. Each iron atom loses 2 electrons to become a ferrous ion, which then dissolves into the surrounding moisture. These liberated electrons flow through the body of the metal to the cathodic sites. At the cathode, these electrons are consumed in a reduction reaction. Typically, oxygen gas dissolved in the water reacts with the water and these incoming electrons. This reaction produces hydroxide ions. The most critical impact of rusting is the significant weakening of the metal itself. As corrosion progresses, it eats away at the material, reducing its thickness and structural integrity. This loss of material directly translates to a diminished ability to bear loads and withstand stresses. This is an especially grave concern for large-scale structures that rely heavily on the strength of their metal components. Consider the extensive networks of pipelines, immense steel frameworks of bridges, or the hulls of massive ships. Even modern buildings often depend on reinforced concrete, where the gradual weakening caused by corrosion can turn these structures into potential hazards. The annals of engineering contain sobering examples of catastrophic failures directly attributable to corrosion. Many tragic events occur where bridges collapse during rush hour traffic due to corrosion damage or poor maintenance. India consumes over 130 million metric tons of finished steel each year. The financial repercussions of corrosion on this steel can be truly immense, creating a substantial economic drain on economies worldwide each year. These costs are not limited to the mere expense of replacing a rusted component. They encompass a much broader spectrum of environmental burdens due to mining and processing of these metals. As a result, industries across various sectors invest vast sums of money annually in corrosion prevention measures and the repair of corrosion-related damage. The true cumulative cost of corrosion often remains hidden from the general public's view. Nevertheless, it significantly impacts national budgets, industrial profitability, and overall economic efficiency, acting as a silent tax on progress. In India, for instance, it has been reported that corrosion leads to an annual economic loss approximating Rs 1.52 lakh crore. This staggering figure affects a wide array of critical sectors, including national infrastructure like bridges and railways, essential utilities such as power and water supply, diverse manufacturing industries, and even national defense capabilities. Experts in the field suggest that a considerable portion of this loss could potentially be saved through the implementation of proper corrosion monitoring systems and timely, effective intervention strategies. The economic challenge posed by corrosion is similarly daunting in other industrialized nations. Confronted by the relentless and costly assault of corrosion, scientists and engineers have diligently worked to develop sophisticated methods of defense. Among the most effective and widely adopted of these strategies is a technique known as cathodic protection. This clever approach is firmly rooted in a thorough understanding of the fundamental electrochemical mechanisms that drive corrosion. The central idea behind cathodic protection is remarkably simple, yet profoundly powerful. It seeks to transform the entire surface of the metal structure that needs protection into a cathode, thereby preventing it from becoming an anode. If a metal surface can be successfully forced to behave as a cathode within an electrochemical system, it effectively cannot corrode. By converting our valuable steel bridge, underground pipeline, or ship's hull into a cathode, we essentially halt its natural tendency to decay and revert to its ore form. Cathodic protection works by strategically shifting the electrical potential of the metal structure in a way that makes the corrosion reactions thermodynamically unfavorable. The discovery, development, and widespread application of cathodic protection represent a significant advancement in the fight against material degradation. It is a fundamentally proactive approach, rather than a merely reactive one. There are two primary methods for applying cathodic protection to metal structures. The first is the sacrificial anodic method, also known as galvanic protection. The structure is connected to a more active metal, which corrodes instead. Common anode materials include zinc, magnesium, and aluminum alloys. The second method is impressed current cathodic protection, ICCP. ICCP uses an external DC power source to protect the structure. The significant advantages offered by cathodic protection technology extend well beyond the mere preservation of metal and the associated economic savings. This innovative approach plays an increasingly crucial role in the broader efforts towards environmental conservation. By effectively preventing or substantially slowing down the insidious process of corrosion, we can significantly extend the useful operational life of existing metal structures. This longevity directly translates into a reduced need for the frequent replacement of these structures. When bridges, pipelines, and storage tanks last longer, we consequently do not have to manufacture as much new metal to take their place. The production of new metal from raw ores is an exceptionally energy-intensive undertaking. Each of these stages consumes considerable amounts of energy. A large proportion of this energy is still derived from the combustion of fossil fuels. Therefore, by decreasing the demand for new metal through life extension strategies like cathodic protection, we achieve a corresponding reduction in overall energy consumption. This, in turn, leads to lower emissions of greenhouse gases, thereby assisting in the global effort to mitigate climate change. Cathodic protection enhances the safety and reliability of structures that underpin modern society. Critical infrastructure like bridges, tunnels, pipelines, and offshore platforms form the backbone of our daily lives. Their failure can lead to severe disruptions, economic losses, and potential loss of life. Cathodic protection ensures these structures remain functional and safe, often beyond their design lifespan. It reduces the frequency of costly and disruptive major repairs. The same principles apply to underground pipelines transporting essential resources. Cathodic protection is a primary defense against corrosion for these pipelines. The journey leading to the development and refinement of cathodic protection is a powerful illustration of the immense potential of dedicated scientific research. This vital technology did not emerge by accident. Rather, it was born from a deep and evolving understanding of the complex principles of electrochemistry. Scientists and engineers meticulously studied the fundamental reasons why metals corrode. They investigated the intricate interplay of chemical reactions, electrical currents, and environmental factors. This foundational knowledge then paved the way for the conception and practical application of innovative solutions like cathodic protection. The field of corrosion engineering itself is a specialized, multidisciplinary domain. It skillfully applies core principles from metallurgy, chemistry, materials, science, and physics. The overarching goal of this field is to control corrosion in the most economically viable and safest manner possible. Within this specialized field, cathodic protection stands out as a truly transformative innovation. It directly and effectively addresses major challenges that are simultaneously industrial, economic, and environmental in nature. In